Welcome back, everybody. So this is our last week of classes, and our goal for this week is to finish the proof completeness, and with that we finish compactness, and we finish everything. Everything kind of comes to a close. So let me remind you, completeness is the theorem that said that if a set of sentences gamma logically implies a sentence phi, in the sense that every model of gamma is a model of phi, then there is a formal finitary deduction of phi from gamma. And we show that's equivalent to saying that any consistent set of formulas is satisfiable, and we are trying to prove completeness via that way. So consistent meant there is no deduction of a contradiction, but satisfiable means there exists a model. So they are very different in form. So we're using the fact that we have no deduction of a contradiction to build a model. And we've been going quite far so far. We built our term model. By taking all the closed terms that you can write in the language. Then consider this equivalence relation of two terms are equal if you can prove they are equal. And then define the function symbols and the relation symbols on this guide. And we proved that if you have a maximal set of sentences, then the term model satisfies all formulas phi so long if and only if they are proved, but only for the case when phi is quantifier free. So what we need to do now is fix the case with the quantifiers. And the example of the groups that we saw earlier, that's a good example where things fail when you add quantifiers. We had this example where we had the group axioms, but we didn't have a term for the inverse. And even though we had the formula that says for every x exists a y, x star y is the identity, that formula did not hold in the term model, mostly because of these quantifiers, mostly because of this there exists. Because just saying that there exists something in the set of sentences doesn't imply that it's going to be a term for that, and therefore it might that y might not be given by a term, and therefore it wouldn't be in the term model. So in the term model you wouldn't have such a y. So how do we fix that? So this is the concept that we add today, which is the fact that containing term witnesses. So we say that a set of sentences gamma contains term witnesses if whenever gamma proves a formula of the form there exists an x phi, where imagine that x is a free variable inside phi, right? So x kind of shows up inside phi. Then there is some closed term t such that gamma proves the formula phi where x is being substituted for t. So you put a t in place of every x inside the formula phi. So that's what we need. So let's see an example of how this would look like, for instance. In the case when we had tau, just the identity, star, and c, and gamma, the group axioms, then let's just put an example. So in this case, gamma shows that there exists a y such that y star c equals the identity. It shows this, right? Because one of the group axioms is that for every x exists a y such that x times y equals the identity. So you can give a deduction proof for this, but there is no term in this our term model that satisfies what this y satisfies, right? We saw that before. No closed term t in this vocabulary such that gamma shows t star c equals e. If you remember, when we saw this example last week, we saw that all the terms that we get built out of e's and c's are essentially e alone, and then all the powers of c star c star c 3 times, because e is identity and c is the only constant you have. All you can do is multiply it by itself, and by associativity those are all the only ones you get, and by identity the e's cancel out. So those are all the terms you get, and you don't get C inverse as a term. So in this case, we see that there is no such closed terms, and therefore this is, tells you that the gamma doesn't contain term witnesses. Good. Let's see another example. Let's look at the other example that we saw last time, which is still the group axioms, but now with the inverse in the language. Right, so in this case, we got tau has the identity star, but it also has an operation, a unary operation for inverse, and then two letters A and B, and gamma is the group axioms. But now the group axioms are built using this inverse operation, right? So the inverse axiom says for every x times x inverse equals identity. So it's a slight modification of the group axioms to describe how this inverse behaves. So now in this case we have again the gamma shows there exists a y star c equals e, fine, shows the same thing, still an axiom, and the closed term, no sorry, it's not a c, should be an a because we don't have a, let's say, and there exists a term, the term a inverse, right? And if we replace y for a inverse, we get the gamma proves a inverse star a equals e, right? So we are replacing the y by a inverse, and it works, right? So we have a witness for that one. So that doesn't mean that it contains term witnesses for all existential terms of this form, but this is an example of one where it exists. Gamma proves something of this form, right? This one has this form, exists y such as something, and then in that something you can replace the y by a term, and gamma proves that. So gamma has a term. Essentially, the name of this comes because if gamma proves, so it could be that you prove there exists x such that something, but you don't know how to name that thing. Well, containing term witnesses, it means that there exists a term in the language, in the vocabulary. I can write with the symbols of the vocabulary, which witnesses, this term t witnesses that there exists an x such as phi, because t is one such guy that satisfies phi. Okay, so let's see what we can do with this definition of containing term witnesses. And here's the key, here's the lemma. If gamma is maximal, consistent, and contains term witnesses, then for every well-formed formula phi, not just quantifier free, but every well-formed formula phi is true in the model, in the term model of gamma, if and only if gamma proves phi. Okay, so maximal, consistent, and contains term witnesses. Then it's satisfied in the term model, if and only if it's proved. Let's compare that with what we proved last time. Last week, we showed that if gamma is maximal and consistent, but we didn't say anything about term witnesses, and phi is quantifier free, so it contains no quantifiers, then it is true in the model, if and only if it's provable. Okay, so we didn't have term witnesses, but we only restricted ourselves to quantifier free formulas. Now we want all formulas, but we are imposing the condition that gamma has to contain term witnesses. How do you prove this? Well, you need to prove it by induction. You start with atomic formulas, and then you have to see how you build the formula to do the previous case. So this beginning of the proof from last week is essentially the same. If phi is atomic, I mean, we have more hypotheses, so whatever we did last week still works. Not because we're still maximal and consistent, like we were last week. So if phi is atomic, then we get that gamma proves S equals T if and only if that's true in the model, and gamma proves a relation holds if and only if the relation holds in the model. So that's good. So those still work. If phi is of the form psi and theta, then we prove that gamma proves psi and theta if and only if psi and theta are true in the term model. If phi is of the form not psi, then gamma proves phi if and only if it's true in the model, and that's where we use the maximality and the consistent, right in that one, very importantly. So those are the cases, and actually we say, well, the other connectives just follow directly from these ones, right? Because they can be defined in terms of this one. So essentially, all we have left is the quantifiers. So let's do that. If phi is of the form there exists an x psi, then what do we have? Well, we have a gamma proves there exists an x psi if and only if there is a closed term t such a gamma shows psi with x being replaced by t. Why is that I say if and only if? So one direction, that direction from left to right, that follows exactly from the property of containing term witnesses. That's what it says, that if you prove this, then you prove that. The other direction, where is the other direction from? Well, the other direction follows from, you can build a deduction of that essentially using that these group 2 axioms by changing, like looking at the contrapositive. So if phi is not alpha, then that thing is equivalent to phi of x with x replaced to t implies there exists x phi. Right? This is just the contrapositive. If you write, so this is equivalent. What I'm saying is this is equivalent to saying not this implies not that, and this is so not this is this, not this is that. So this is just a particular case of this group 2 axiom that we are using right here. If you can prove this, then using group 2 and model exponents, then you can prove this. And essentially it's obvious, right? Because you have the witness right there, so that should be the case. So follows from there, you get this equivalence. And now, once this is true, now we can use the induction hypothesis, because that's a smaller formula, at least it has one less quantifier, to get that this is true if and only if is true in the model of terms that psi is true when x is replaced by t. Alright, but then now this is just again definition of what it means existential to be true. So that means when you replace x by this particular, the interpretation of t, that's what you get. So essentially, maybe I'm gonna write this as then it's true, psi is true where x is interpreted as the equivalent class of t that belongs to the term model. And then by definition of what it means to satisfy an existential, that's the same thing as saying that the term model satisfies there exists an x psi. Right? So we get exactly what we want. You satisfy this if and only if you satisfy. This is true in M. So that finishes the proof, because, well, the for all case is you can be defined for all out of there exist. So it's gonna work. It's followed from this case, right? For all case, for all is definable from existential as not exists not. So that's it. So we get that if you're maximal and consistent and contain witnesses, then the term model satisfies all the formulas in gamma. So that's almost what we want, because we want to show that if you're consistent, you're satisfiable, and we have shown that if you're consistent, maximal, and contain witnesses, then you're satisfiable by the term model. But we have extra assumptions that we didn't have in completeness. It's maximal and contains witnesses. So this only works when you're maximal and contain witnesses. So the next step is to show that if you have sigma that is consistent, then there exists an extension of it. An extension in the sense you add more formulas, sentences to it. And actually we're going to increase the vocabulary too. So it's a bigger vocabulary and a bigger set of sentences where gamma is maximal consistent and containing witnesses. So we can make it bigger to make it maximal consistent and contain witnesses. Then this, together with the lemma, completes the proof of completeness. Right? Because now when we start just starting by something that is consistent, we can first extend it to something that is maximally consistent and contain witnesses. Then we use the lemma to show that term model of that gamma satisfies everything in gamma, and in particular it satisfies everything in sigma. So we have built a model of sigma. Okay? So those are going to be the two steps. First, make it larger so that it's maximally consistent containing weaknesses, and then use the lemma to show that the term model of that one satisfies gamma and therefore sigma. So that's what we're going to do in the next video to show that this theorem holds. See you in a bit.